Tim loves skateboarding, but a skateboarding trick gone wrong lands him in the hospital with a compound tibial fracture. He's told that he needs a bone graft to help him heal, but a worried Tim wonders, bone grafts, what are those? I'm Avantika.
And I'm Ziting. We are students from Singapore and we are excited to share more about our research on the biological evaluation of calcium phosphate and collagen bone grafts for bone defect healing today.
Bone grafts are typically used to heal critical-sized bone defects. There are three broad categories of bone grafts. Autografts are currently the gold standard because they're osteoconductive, osteoinductive, and osteogenic. Similarly, allografts from donors allow for greater quantities of bone to be obtained, but come with some disadvantages such as donor site morbidity and increased immune reaction risks. This is where synthetic bone grafts come in. Our study focused on calcium phosphate collagen or CAP collagen composite grafts, which consist of CAP granules that are held in place by collagen fibers. Both calcium phosphate and collagen are widely used biomaterials owing to their ability to mimic the natural composition of bone.
Using a graph with two different components led us to first ask if CAP to collagen ratio affects the biological performance of the graft. We questioned this since CAP and collagen have different bone formation abilities and degradation profiles. To assess biological performance, we looked at two main parameters, material resorption and bone formation. If CAP to collagen ratio indeed influenced defect healing, we then wanted to know which ratio would result in the best biological performance. This would mean the material degradation rate complements the bone formation rate, and the bone formation rate itself is high. This would ensure that the scaffold does not degrade too slowly or too quickly. We hypothesized that higher CAP to collagen ratios will better promote bone defect healing due to CAP's osteoconductive properties.
Moving on to our methods, three different scaffold ratios were prepared prior to our project: low, mid, and high CAP to conduct both in vitro and in vivo studies. In the in vitro study, we carried out a degradation assay on different scaffolds with and without collagenase in conditions that mimic the in vivo environment and measured pH over a week. For the in vivo study, we analyzed micro-CD images obtained from the animal study using C10 software. We also histologically evaluated these samples by preparing stained and sectioned slides.
Here are our key findings. For the in vitro data, there are clear differences in pH change amongst the three ratios for both with and without collagenase. Low and mid CAP show an initial increase in pH, possibly due to residual NaOH from scaffold preparation, while the pH for high CAP remains relatively constant. pH decreased to a greater extent for low CAP than mid CAP, indicating that the enzymatic degradation of collagen produced acidic end products. Interestingly, some studies state that the end products should be neutral rather than acidic. Therefore, the mechanism behind collagen degradation remains unclear. In Figure D, the low CAP scaffold shows CAP granules falling apart from the main structure, indicating that it has low mechanical stability.
Micro-CD scans allowed us to visualize high-density tissue, which consists of both hard bone tissue and CAP material from the scaffold. These two parts cannot be differentiated owing to their heights very similar X-ray attenuation values and hence appear as white regions. Graph 2b shows that the percentage of high-density tissue remains relatively constant both prior to and post-implantation. Since we can observe trabecular bone within the region of interest, we can then deduce that material resorption and bone formation had occurred in parallel over the course of 12 weeks. Through histological evaluation, we were able to observe and quantify the CAP resorption and bone formation that had occurred. More bone formation is observed in the high CAP scaffold, and this is also supported by numerical data as shown in Figure 3b, where there is nearly twice as much bone formation in the high CAP scaffold than the low CAP scaffold. This trend is supported by literature which states that CAP has osteoconductive properties. Degradation rate of calcium phosphate was calculated using the formula shown here, where the initial material percentages obtained from micro-CD of the unused scaffolds and the final material percentage from histological evaluation. Surprisingly, CAP degradation rates did not appear to be influenced by CAP collagen ratio, and this can be explained, however, by the fact that the same CAP type was used across all three ratios, and current literature suggests that only factors such as chemical stability and solubility, which depend on the CAP type, influence the degradation rates in an in vivo environment.
Overall, we can conclude that the CAP to collagen ratio does influence bone repair both in vitro and in vivo. In vivo results also suggest that higher CAP to collagen ratios perform better. Our results demonstrate that there are various intricate factors at play which influence composite bone graft performance.
Future research directions could include the addition of growth factors in human mesenchymal stem cells and also investigating whether other types of calcium phosphate and collagen yield similar results. Though still a work in progress, optimizing these synthetic bone grafts allow people like Tim to benefit from them. We've come to the end of our presentation. Thank you for listening.